So originally in the syllabus, the first exam was scheduled for a week from today, but I don't want to rush through chapter 3 in 2.5 days. So, and I'll post an announcement on Brightspace after class. So I'm going to move the exam from that Friday to the following Monday, so that we have all of next week to work on chapter 3. We're going to start it a little bit today, okay? And I'll also adjust the homework due dates accordingly. I'll extend those. And Ben pointed out that there's some wackiness going on with it marking things as late that aren't late yet. So I have to fix that. And that's maybe an artifact of Dr. Vining and I are for the first time using that automatic function that allows people to put things in late. So we don't know exactly functionally like all the quirks of how it works. So we may have to just change it. But so don't worry, like nothing will be marked late up to this point. So we will fix that. All right. Any questions? Any other questions to start out today? All right. So what we're going to do is we are going to finish our tour of the periodic table, and then we'll go into the unit of the mole. And unfortunately, I brought the wrong box and left my moles behind, but that's all right. We'll do it anyway. And now this is appearing. All right, here we go. I think this is the universe's way of telling me I just should not have gotten out of bed this morning. Hang on for a sec. Okay, go back into that. All right, we're back. Okay. All right, so the periodic table, we've talked about what the rows and the columns mean. Okay, so the rows are what we call the periods, and your properties of your materials, the physical properties, okay, are going to be varying as you go from left to right, okay, in a periodic, predictable fashion. Okay? And as we get into the next chapter, okay, we're going to elucidate, we're going to clarify the relationship between the row that an element is in, okay, and energy levels within the atom itself. So differences between electron energies in elements, okay? All right, so the columns are what we call the groups, okay? And those are, when elements are in the same group, they behave chemically in a similar fashion. But again, as you go down a group or up a group, you're going to have regular, predictable changes in properties, whether it be reactivity, whether it be atom size, attraction for electrons, and things like that. All right, so let's talk about a subset of the groups on the periodic table, which have been given special names. Okay, so we're going to be talking about groups 1A, 2A, 7A, and 8A. Those are the big four. Okay, and then group 6A also has a name, but it's used less frequently. Okay, so all right, so group 1A, we call those the alkali metals. Okay, and when we say something is a metal, okay, we can break the periodic table into three regions based on physical properties, okay? So you'll notice this, I'm going to make this a little bit fatter for the moment. All right. So this kind of staircase here that you see, okay, that breaks the periodic table into everything to the left we consider metallic or metals, and the things to the right we consider nonmetals. Okay, and there's elements that are kind of in between. Okay, we call those metalloids. So what you'll notice is everything that's in blue here, okay, is considered a metal. Okay, so the properties of metals, okay, are, again, they're physical properties. Okay, so they're shiny. Okay, they're what we call ductile. If I took a sample of, let's just say you take a chunk of aluminum or a sample of aluminum foil and you whack it with a hammer, okay, it's not going to break apart, it's going to kind of squish, right? So those are what we call ductile, okay, so they're not brittle. You can kind of, using physical pressure, you can move them in, you can shape them into different shapes like wires or things like that, okay? They're good at conducting both heat and electricity. Conduct heat. So again, anything that's on the left side of the periodic table that's shaded in blue in this version is what we would consider a metal, okay? When we, and now the things that are kind of in this orangey color here, right? Those are our nonmetals. Okay. And nonmetals kind of have the opposite property of metals. Okay. They tend not to be shiny. Okay. So they tend to be dull if you have a sample of them, or brittle. So if it's a solid, okay, it's going to be, if I took a sample of solid carbon, okay, imagine, you take a piece of charcoal and you smash it with a hammer. Does it stay in one piece and flatten out? Or does it break into lots of pieces, right? So that's an example of how nonmetal behaves. It breaks into lots of pieces. It's brittle, okay? And they don't conduct electricity very well, okay, if at all. And they're what we would call insulators. Okay, so they're going to not conduct heat very well. Now, most of the elements on the periodic table, if we're talking about their properties, okay, most of them exist in solid form, okay, although there are a couple exceptions. Okay, so there are two elements that exist as liquids under, normal atmospheric pressure, room temperature. Okay, so, oops, this is getting in my way. All right, so most elements are solids. Does anyone know the two that exist as liquids normally? Yeah. Gallium actually is a solid at room temperature, but it melts very, very easily. So that's the one that's like the third liquid one, but it has to be like if you're down in Florida in the summer kind of thing. So yeah.
Is bromine one of them?
Bromine is one of them, and mercury. Yeah, so bromine and mercury are liquids, and we'll give gallium its credit. We'll say gallium, if it gets warm, gallium will melt in your hand, if so, body heat kind of thing. All right. Now, there's a number of elements that exist as gases, okay? And so that gets us to kind of the next one of our groups with names, okay? And that is group 8A over here. They're called the noble or inert gases. So let's talk about the difference between, again, the alkali metals and the noble gases. They're at opposite ends of the spectrum, okay? One are, our ductile, shiny, reactive, chemically, or electrically and thermally conducting solids, okay? And then on the right, okay, we have the noble gases. Presumably they were given that name noble because back in the 19th century, when the periodic table was being put together and we were naming these things, people who were in the nobility did not mix with the common folk. And the key feature of the noble gases is that they are what we call inert, which means they are very chemically not reactive. Okay? So they're unreactive. And again, they exist in gaseous form. And again, as we get into, Ben.
Is that because the outermost shell is completely full of electrons?
Yep.
It's normal state, at least?
Yep, and so that's so once we talk about electronic structures, we're going to talk about why those are unreactive. And they're unreactive because all of their electrons have kind of filled in the energy slots and everything is in a kind of stable, filled in state. There's no kind of empty holes that they're looking to fill in terms of electrons within the atom, okay?
So all noble gases are non-reactive?
Yes, all noble gases are non-reactive, okay? So, and we tend to use those, so for example, argon right here, okay? When you are with certain types of instrumentation, okay, if you're trying to analyze a chemical, that's what we call volatile, okay, and it's going to evaporate, and when we use instrumentation, there's something called gas chromatography, mass spectrometry. So these techniques, okay, rely on having your material that you're analyzing go into the gaseous state, but you have to have something that's going to move it, okay, through the instrument that's going to do the analysis so that it can analyze those molecules. And so the things that you do, okay, to help it move through, okay, you're kind of taking this gas and blowing it through your system. And so what you do is you have what we call a carrier gas, and you want the carrier gas to not react with the molecules you're trying to analyze, okay? So what you'll find is helium and argon are often used as carrier gases in these instruments. Argon's a really popular one. So you can use the argon gas, those molecules, you can use them to kind of push the other molecules through your system without having them react with that. Okay, so this is a good, what we call carrier gas in chemical instruments. Okay. All right. So if the noble gases are unreactive, they exist as gases, then our alkali metals are the opposite. They're very reactive. Okay. And again, they're kind of the most reactive things on the periodic table. Okay. All right. So I said that most things are solids, okay, but some elements are gases. There's one other group. Oh, yeah.
What's the last part of what you wrote for argon?
Argon is a good carrier gas in chemical instruments. All right. So elements that exist as gases are, again, group 8A, that's our noble gases, and group 7A. Most of them, okay? So group 7A, okay, we know that bromine, again, this is one of our exceptions in terms of it exists as a liquid, okay? And you can have iodine as a solid, but it goes into the gaseous state very easily. So the halogens are the name of this group, okay? And so those will exist, okay, as gases or as, easily gasified, if you will, solids, okay. The halogens are interesting in that they exist as what we call diatomic molecules. So if you're looking for, a sample of chlorine, okay, pure chlorine is going to exist as Cl2 chlorine gas, okay? So the halogens are also fairly reactive, okay? Because they're very close to being noble gases, okay? And so the idea when we talk about electron configurations is they're going to engage in reactions to get to an electron configuration that looks like the noble gases, okay? So they are reactive and they exist as diatomic molecules. So for example, Cl2, okay, so chlorine. Now, there are other elements, okay, that you can find as gases, okay? Can anybody think of two other elements that exist as gases? Take a deep breath and think about it. Oxygen, yeah. So now oxygen can exist in many different forms. Okay, so in a couple slides, we'll talk about something called allotropes. That's when you have a pure sample of an element, okay, that can exist in multiple different forms. Okay, so O2 is a gas, nitrogen is a gas, right? But you can find samples of those elements in other forms as well, okay? So ozone is pure oxygen as well, but it's O3, okay? All right, so who have we got so far? So we've got our noble inert gases, we've got our halogens, and we've got our alkali metals, okay? So the next group, or the last group really that we're going to talk about in terms of names, okay, are right next to the alkali metals, okay? Those, that's not what I wanted. I wanted this. These are called the alkali earth metals, or the alkaline earth metals. And the alkaline earth metals are also quite reactive, but they are less reactive than the alkali metals, okay? So they're less reactive than group 1A, okay? But when they react with water, okay, they're called the alkaline earth metals because when they react with water, they make an alkaline or basic solution, okay? So, and both group 1A and 2A, both the alkali metals and the alkaline earth metals, both of them will react with water and make a basic solution, okay? then in a couple chapters, we'll be talking about acids and bases, okay? So right now, bases, think of them as the types of solutions that you would typically use to clean things, okay? So bases are slippery and they're caustic, okay? So, all right, so the one thing that we haven't talked about yet, so we've talked about our 4 big group names. The other group that we can talk about is group 6A, which are known as the chalcogens. Chalcogens. And that's the group that has, oxygen in it, okay? But again, it's kind of less frequently that we talk about those by their group name. All right, so the final thing on in terms of kind of classifying the materials by their properties are these elements that are right here, kind of on the interface between the metals and the nonmetals. And what you'll see, those are in green, okay? And those are called the metalloids, okay? So metalloids, okay, do conduct electricity, okay, but not as well as metals. So notice that silicon falls in the metalloids. It's one of the metalloids. And again, silicon is what, is considered a semiconductor. Okay, so it conducts electricity, but not like super, super well. And it's a key component of any of our electronic devices. Okay, so computer chips are made with semiconductors. Please show up. And silicon is the material, again, that is most commonly used for that. All right. There we go. All right. So let's just make a few notes about our metalloids. So the metalloids are the things in green, okay? And they conduct electricity poorly, but again, they still conduct electricity. And again, their physical properties are somewhere between a metal and a nonmetal. So silicon, oh yeah.
What are the 2 gray ones?
The 2 gray ones? So, yeah, ununceptium and ununoctium. Okay, so these are, look at their atomic numbers, okay? They're really big, right? And what did we say about elements whose atomic numbers are above 83? Their nuclei are, they're radioactive, their nuclei are unstable. And when we get into the hundreds, okay, those are all elements that you can't go to a mine and dig them up. They're things that were made in a lab, in a particle accelerator, and they existed for, maybe milliseconds. And somebody said, hey, I discovered a new element, but we don't know anything about their properties, okay? So in the case of these, okay, we can't really classify them because we haven't verified that they have those properties, okay? They're in the group because of their electronic structure. They're in the row also because of their electronic structure. But in terms of their properties, not been verified. What's that?
Are they gases or halogens, or are they?
It's hard to say. It's hard to say. Again, so it's gone again. Ah. To be on here that it's. I am not having luck with this today. There light is on, but nobody's home. All right. Come on. Sorry, guys. There we go. All right. So again, you can't really say, this is a gas or this is a gas. I mean, their electronic structure puts them in those groups. If we were able to get enough atoms of that material, we would predict that it would be an unreactive gas or a reactive gas. But it's really hard when you have to artificially make an element and you've only made one or two odd atoms of it. And they disappear because they're so unstable, they disappear in, in milliseconds or microseconds. So you can't, again, the materials that are going to do chemistry, okay, are kind of the things that are up here, okay? And then these materials here, the things with the really high atomic numbers, people make as intellectual exercises kind of thing. Again, so we're going to be focusing on really mostly the things in the first 4 rows of the periodic table, okay? And those are the ones that have the most predictable behavior, okay? Once you get to larger elements, because they have those unstable nuclei, that affects their chemical properties as well, okay? All right, let's see. So we talked about the names of the groups. We talked about their properties. We talked about the metalloids. So the metalloids, again, their properties are in between, okay? In between the metals and the nonmetals. So for example, silicon, it conducts electricity like a metal. But silicon itself is a hard, brittle material, like a nonmetal. So it's one of these somewhere in between. So things to the right of the metalloids, are firmly nonmetals. Things to the left are firmly metals. And then these guys in between, have some properties of each, okay? All right. All right, and I just talked about those, so let's move on to, the structurally what elements would appear like, okay? When we have metals, again, they're going to typically exist as solids where the atoms are in this regularly packed arrangement, okay? And different metals will pack in different shapes. So you can imagine something packing like a set of cubes and another element packing like maybe in a honeycomb pattern. There are things that we call space groups that if you studied in organic chemistry, you'd spend a lot more time on, okay? But when we look at kind of microscopically how the atoms arrange when we have a sample of this element, okay? We have, close packing and kind of regular arrangements that can be different shapes, okay? So.
For all the blue ones?
Yes. Yep. So for our metals, when they're, again, when they're solids. Okay. All right. Okay, so the noble gases, okay, again, they're so unreactive that they just exist as individual atoms and, again, in the gaseous state, so individual atoms that stay pretty far away from each other. Okay, so remember that these are unreactive. And then our halogens are group 7A. That's this group here. And hydrogen, oxygen, and nitrogen are going to exist as diatomic molecules. Okay? Some of them can exist in other forms as well, like oxygen can exist as O3. All right, and let's see. All right. So discrete just means a single separate thing. Okay.
Oh, that's the same as the unreacted chemical?
Yeah. So discrete means kind of a single separate entity. So if to kind of contrast what that means in terms of like compared to metals, with the metals, notice that if you have a sample of the metal, all the atoms are like close packed together. They stay together, and you get a chunk of a whole bunch of atoms. Whereas when we say something can exist as a discrete molecule, it's not necessarily going to be in a form where it's closely packed against other things. Okay. All right. All right. So I said that oxygen can exist in a couple of forms, and we call those forms allotropes. Okay, so we're now going to look at a couple of other allotropes. Okay. So here are, again, we're talking about pure elements. Okay, so when we talk about pure elements, it just means only one atom type in our material. All right. And so if we look at it, okay, over on the left, okay, we've got two separate allotropes of carbon. Okay, so these are allotropes of carbon. And so we have diamond on the left and graphite on the right. So you'll notice the materials themselves have vastly different properties, right? Diamonds are the hardest substance, known on Earth. They're sparkly, they're shiny, and graphite, okay, is a dull gray material that can, kind of easily be kind of taken apart. And if you look at on the atomic level, okay, every one of these circles is an atom of carbon. Okay, so these are atoms of carbon. So both of these materials are made of carbon atoms and nothing but carbon atoms. It's just they're arranged differently. Okay, and so in terms of carbon, okay, you can actually convert graphite into diamond and back and forth. It's just that you have to go over this really huge energy barrier to do that. So it happens really slowly over the course of like millions of years. Okay, so naturally, okay, the way diamonds are produced, right? You've got carbon, and it's down in the ground under all these pressures over millions of years. We can now do that. We can now make what are called artificial diamonds or lab-created diamonds by heating up graphite really hot and putting it under very high pressure. Okay, and you can grow a diamond. Okay, because you're just taking your carbon atoms and you're letting them rearrange to form another allotrope. Okay. All right. So another example of an allotrope is phosphorus. Okay, so these are allotropes of phosphorus, and you can get some really different properties of phosphorus if you arrange the atoms different. Okay, so the one property that should be obvious as you look at the images, so these are all different allotropes of phosphorus, okay, is they're different colors. So we have white phosphorus and blue phosphorus and purple phosphorus, okay? And And, these three forms over on the right are pretty innocuous. They're not very harmful, okay? But white phosphorus is a super dangerous material, okay? It's highly reactive. It's toxic. It's going to burn very hot, okay? So this is kind of a toxic, hazardous material. And again, you haven't changed the atoms, you've just changed the way that they're arranged, okay? All right, so that's what allotropes are, okay? All right, so if we just look at the periodic table, okay, and we think about, okay, whether something is a metal or not, okay, or whether it has metallic properties, okay. Let's think about, again, moving around the periodic table, because the whole point of the periodic table is to allow us to kind of predict properties based on position related to other elements, okay. So, first of all, okay, let's think about if we're moving right or left on the periodic table. Okay, and just going based off of the colors alone and what we've talked about the colors meaning, okay, when you go from left to right, do you get more metallic or less metallic? You get less, right? So if we're asking, whether the metallic character increases, okay, that's going to increase as you go to the left, right? Okay. So that increases as you go left. All right, how about, now let's think about top down, okay? And, for this, we have to look at a particular region of the periodic table, right? Where we actually see colors change as you go, up or down. So where are we going to be looking? On the left-hand side, the middle, or the right-hand side? Yeah. We're going to look at the right, kind of this region right here on the right-hand side. Okay, so if we're thinking about metallic character increasing, okay, would we say it increases as you go top down or bottom up? So which direction are you traveling to get to the blue? We're going down, right? Okay, so our second thing is going to be, as you go down, okay? So the metallic character of an element is going to increase as we move left and down, okay? And again, what you find, okay, you're going to be doing a periodic properties lab, okay, where you're going to be taking some samples of alkali metals, okay, these guys right here, okay, and you're going to be putting them in water to see how they react, okay? And if we think of a metal as being a reactive material, the more metallic you get, the more reactive you get, okay? So that would predict, okay, that if we take, lithium and sodium, okay, it would predict that the sodium would have a more violent reaction with the water than the lithium, right? And some of you may have seen, the YouTube videos where they throw cesium in a bathtub, and whether or not those are real or kind of artificially created, they get this big explosion, okay? So you get more reactive as you go down the group, okay? And that's kind of reflects that more metallic character as you go down the group, okay? All right. Okay, so I'm going to, does everybody have a periodic table with them today? I've got them up here if you need one. So gather around with your neighbors, and we're going to think about putting together some of the concepts we've talked about with the periodic table. And the fourth question is one that I will put up in a minute. All right. While you guys are discussing these questions, I'm going to put up the fourth question, an image for you. All right. So, next week in lab, you guys are going to be doing a spectroscopy experiment where you're going to try to figure out how much copper is in copper ore, okay? And so these are 3 pieces of copper ore that came from Bisbee, Arizona, the home of a retired photography professor here that Dr. Vining went to visit. And so you guys get to vote on which one of these we smash and dissolve in nitric acid this weekend. So each group should come to consensus and cast their vote for either Sparkles, Pointy, and Jed. I just named them based on what I thought they looked like. So anyway, so that's your fourth question for the day. And I'll give you another minute and this one is just icing on the cake, but yeah. Yeah. Well, that's good. I'll be around, yeah. Yeah, I saw your email this morning. Oh. Yeah. We just shouldn't have gotten out of bed. Yeah. All right. Since we have 2 minutes left, I want to go over the other questions. But first, let's do by noise making. Take a quick poll of how people are voting. So, if you're voting for Sparkles, give a cheer. All right. Who wants to vote for Pointy? Oh. How about Jed? All right. It's looking like Sparkles is going to win, I got to say. All right. Okay. So let's get back to these. So what is the name of the halogen in the fourth period? Yeah. Bromine. 1, 2, 3. Bromine is the third one down, but it is the fourth period. So yeah, it's because there's an extra row that doesn't have. So, yep. So bromine is the halogen in the fourth period. All right. So let's think about who's going to be better at conducting electricity. Magnesium. Okay. So magnesium, alkali earth metal. Sulfur, chalcogen. Magnesium. And again, magnesium because it's a metal, okay? And sulfur is a non-metal, right? All right. Okay, so how many protons are found in the element in group 5A, period 2? So go to period 2. Go to group 5A. What's our element? What's the name? So we've got 5A, group 2 is nitrogen, right? And what is the atomic number of nitrogen? 7. Yep. So that means it's got 7 protons. All right, so that brings us to the end today. So we haven't had time to go into the mole. What I'd like to do, okay, is I will do a very quick on Monday, like overview of the mole, and we'll do some examples, okay? But there are like two like YouTube folks who I really like. This guy, Dr. William Comer, is one of my favorites. I love his like explanations of things. He goes a little deeper into why we use the unit of the mole, but this is about a 7-minute video. It's posted in the chapter 2 extras. The link is posted on Brightspace. If you can watch that before Monday's class, that'll help us quickly get to doing some practice problems, okay? And he gives, again, both an explanation of what a mole is and kind of a view as to, by the end of the semester, how we're going to be using that concept, okay? All right. Have a good weekend, everyone.